Hello, today we're going to be looking at our practice test for Chapter 8 in FST, beginning with graphing the cube root of x minus 2 and stating its domain and range. One of the things that we have been doing with these is just making a table for a plain cube root of x, and then looking at how to shift that around. So in this case with the minus 2, we would shift our graph down 2. So our basic points that we would use, we like to pick x values that cube root nicely, so that's where we get the -8, -1, 0, 1, and 8 from. When we cube root those, we get -2, -1, 0, 1, and 2, but then we have to shift those down 2. So those are the points that we come up with here, and I tried to make little green X's on those so we could see those, and then we draw our curve through those points, and you can see the ordered pairs for the final points we end up with on those. Domain and range for cube root functions will always be all real numbers, or negative infinity to infinity in interval notation. We'll take a look at a square root graph. When we're looking at the square root of x plus 3, that plus 3 being in the radical there is a horizontal shift. And because we're adding 3 to the x, that actually moves the graph to the left 3 from where it would be. So that pulls it to the left 3. Again, we've been making a table for just the basic square root of x. So we pick x values that square root nicely. So we started with 0, 1, 4, and 9. And the square roots of those are 0, 1, 2, and 3. So we take those points that would be around here and we pull them left 3. And we get these points here. Again, you can see the ordered pairs that we come up with. Now, domain and range for square root functions is limited. If you look at your domain, again, that's the values for x that can happen for that function. So in this case, the furthest to the left this graph gets is right here, and it does not go any further left than that. So it's this point and to the right. So that's at -3, and it goes all the way up to infinity. Notice we use the square bracket there to indicate that the -3 is included in that domain. Again, part of the reason there's a limited domain is because you can, if you try to square a negative number, you do not get a real number answer. The range is also limited. Again, from this point, the graph does not go any lower than that point. So the lowest point it gets to is 0, and then it goes up from there. Now it does continue to go up forever, so the graph does go from 0 to infinity, again with the 0 getting the square bracket to show that the 0 is included in that range. Looking at simplifying a root here, again the square root of x to the 8th power. Again, remember we don't generally put that 2 there, but it is there. So if you look at that as a rational exponent, it's 8 divided by 2, which of course is 4. Now, technically there would be absolute value symbols there. However, we then say that they are unnecessary because x to the 4th can't be negative anyway, so we don't actually need the absolute value. So we're actually looking at just plain x to the 4th as the answer for that one. Continuing on here, we've got another expression to simplify, so it's the 4th root of x to the 28th power. So again, if we convert that to rational exponents, we get x to the 28/4 power, which would be x to the 7th. In this case, we do need the absolute values, because x to the 7th could be negative, whereas the 4th root of x to the 28th power cannot be negative. So that's why we need the absolute values for that one. For number 5, we just want to write that with radicals, and at this point, and from this point on, we're going to assume that all variables represent positive real numbers, so we don't have to worry about absolute values anymore. There's not a whole lot to this question, just mainly checking to see that you understand that the 9 is the index on that radical, and that the 8 is the exponent on the radicand. I noticed I apparently was goofing around there because I got, for some reason I wrote 9 here instead of n. That was kind of silly. So fix that. So this should really be an n here. So 8m plus n to the 8th power, not 8m plus 9 to the 8th power. It's probably just confused with the 9's and n's there. Alright, looking at the next one. So in this one even gives you a hint. First convert to rational exponents, and again still assuming all variables represent positive real numbers. So kind of a string of work here. So the 7th root of x squared would be x to the 2/7. 9th root of x squared would be x to the 2/9. Now from there we use our quotient of powers property, which says that we subtract our exponents, specifically the one in the numerator from the one, or sorry, the one in the denominator from the one in the numerator. But in order to do that subtraction, we would need a common denominator. Now, of course, you could just type this into the calculator, hit enter, and have it converted back to a fraction for you. But we end up with 4 over 63. And again, since it doesn't tell us to write it as rational exponents, and we started with radicals, then we would end in radical form, so that's where we switch from here to the 63rd root of x to the 4th power. Here, again, using rules of exponents to simplify, write the answer with positive exponents, assume variables represent positive real numbers. One way to look at this one is to change from the exponents to a radical. So the 1/4 power would be the same as the 4th root. And then we just have the 16, the k to the 4th, and the m to the -8th. And you could deal with this negative exponent here or later. At this point, I just decided to keep the negative exponent. And this one actually works out fairly perfectly because the 4th root of 16 is 2. You can 4th root k to the 4th, you just get k, and you can 4th root m to the -8th, you get m to the -2. Now, we can't have a negative exponent in our answer, so we use the negative exponent property to drop the m squared down to the denominator. So 2k over m squared is what we end up with for that one. With number 8, they want us to write it with rational exponents and then apply the properties for exponents, assume that all radicands represent positive real numbers. They do want the answer in exponential form, so that's why we did not switch back to radical form. So what we do first is this 5th root of w is w to the 1/5 power. Cube root of w would be the same as the 1/3 power. So we get w to the 1/5 to the 1/3. So that's the power of a power property of exponents. So we multiply those exponents together. So 1/5 multiplied by 1/3 would be 1/15. So we get w to the 1/15. If they didn't want the answer in exponential form, you could convert that back to a radical. It would just be the 15th root of w to the 1st power, or just plain w. So, but again, they did ask for that in rational exponent form. That's why we left it like that. Looking here, we want to multiply these radicals together. Because they are both cube roots, we can use our product rule, which says we can just multiply the 25x by the 49x, and we get the cube root of 1,225x squared. That cannot be simplified. Again, looking at those factors of 25 and 49, you'd see that you don't have any factors repeated 3 or more times, and the x squared has an exponent that's less than a 3, so none of that can be cube rooted actually. For number 10, simplifying this radical, again assuming variables represent positive real numbers. So the cube root of z squared over 216, again I would start by thinking of it as a radical in the numerator and a radical in the denominator. The cube root of 216 is just 6, and then we can't do anything with the cube root of z squared, so that's all we have for that one. Number 11, we want to simplify this radical, so we'd be looking at splitting this up. Again, notice too this negative sign just kind of go along for the ride for this problem. 147, kind of a tough split, but it does split as 49 and 3. So that's where we get the 49 and 3 from, because that gives you 147. K to the 7th, again we can't square root that, but we can square root k to the 6th. That leaves us a single k over here. And we can square root q to the 8th, so that's why we have all of that here. When we do square root this, again we still have that negative, and then 7k cubed q to the 4th, and then just that square root of 3k still in the radical there. So there's what we come up with for that one. For number 12, again same sort of thing, we're splitting up a cube root. One thing you could do too here is that this negative could just be pulled out, because you can do that with odd roots. I just decided to keep it as a cube root of a negative 64 since we can cube root that. Again, with the a's, again, what we're trying to do is we're trying to get the exponent to be a multiple of 6. So the highest multiple of 6 that's less than or equal to 8 is, or sorry, multiple of 3 is 6. So that's why we chose a to the 6th. Likewise, the highest multiple of 3 that is less than or equal to 5 is 3. So that's why we took a b cubed here. That leaves us with an a squared here and a b squared here. That way we get a to the 8th and b to the 5th, respectively. We can then cube root that first radical. We get a negative 4a squared b, and then the cube root of a squared b squared we can't do anything with, so that's why it just stays like that. Let's see. So cube rooting y to the 13th over 125. Again, I would start by thinking of it as cube root over a cube root. Cube root of 125 is 5, and the cube root of y to the 13th, again, 13 is not a multiple of 3, but the largest multiple of 3 that's less than 13 would be 12, so that's why we split it up as a 12 and just a plain y, or y to the 12th, I should say. And then you cube root y to the 12th, and you get y to the 4th, so we still have that y to the 4th times the cube root of y over 5. That's what we're looking at for that one. Alright, taking a look at number 14, they kind of give you a clue here as how to go about this one. First write the radicals with the same index and then multiply. So I like to convert to rational exponents, 1/2 and then 1/3, and then write them both as sixths. So 3 over 6, 2 over 6, and then we can, so it would be the 6th root of 3 cubed, that's where the 27 comes from, the 3 cubed, and be the 6th root of 4 squared, that's where the 16 comes from is the 4 squared. They're both 6th roots, so we can multiply the 27 by the 16, we get 432, and again with those factors of 27 and 16, there aren't enough repeated factors to simplify or 6th root any factor from there, so that's why it just stays as it is. For number 15, we do have to simplify that square root of 50 before we can do anything else. So we split that up as 25 and 2. Square root of 25 is 5, so 9 times 5, and that gives us 45. So 4 square roots of 2 minus 45 square roots of 2 is really negative 41 square roots of 2 for that one. For number 16, we need to rationalize that denominator. So we multiply numerator and denominator by the square root of 3. That's where these come from. We have to kind of figure that out. And then we get the square root of 3x here still minus the square root of 3x over 3. Now the reason this 3 over 3 is here is because in order to subtract these we need to have a common denominator. Here we've got a denominator of 3, that's why 3 over 3 here. That leads us to 3 square roots of 3x over 3 from here, minus really 1 square root of 3x over 3 here. They are like terms, they're square roots of 3x, they have a common denominator. 3 minus 1 is 2, so 2 square roots of 3x over 3 for that one. So kind of a bit going on there. For number 17, rationalizing the denominator. With this one, with a square root of 49, I would go ahead and square root that. So we get 7 over the square root of 6. To rationalize that square root of 6, we multiply numerator and denominator by the square root of 6. So we get 7 square roots of 6 over 6. With number 18, since the numerator does not square root perfectly, I would focus on rationalizing the denominator first. So really I'm multiplying by a square root of y over square root of y. I kind of just snuck those in under that radical that was there. So that does change the numerator a little bit, changes the denominator to the square root of y to the 6th, which we can do. That's where the y cubed comes from. And then in the numerator we need to simplify that. Well, it looks like maybe I lost my negative along the way there, so put that back in. So we split the 98 as 49 and 2. So that's where the 49 and 2 come from. And then the x cubed we split as x squared and x, and then the y, there's not enough to square root that. So we end up with then the negative 7x from square rooting the 49x squared, and then the square root of 2xy over y cubed. For number 19, again trying to simplify this cube root. So in order to simplify that, really what we have to do is rationalize the denominator. Again, it's a little bit different rationalizing a cube root rather than a square root. So what we're trying to do is turn the 5 into a perfect cube. The first perfect cube that is a multiple of 5 is 125, which is 5 cubed. So in order to get the 5 to become a 125, we have to multiply by 25, which of course would be the same as 5 squared. In the numerator, we end up with the cube root of 175, which we cannot simplify at all. And the denominator, cube root of 125, which again is a perfect cube, so we get 5 for that. For number 20, again still trying to rationalize a cube root, so a cube root of 6x over y, so it doesn't simplify at all on its own, so we have to add in there a cube root of y squared. We do that to both the numerator and the denominator. And again, by add in, I really mean multiply. So that gives us a cube root of y cubed in the denominator, cube root of 6y squared in the numerator. Again, there's nothing that can be done with that numerator, so it is just what it is, and then the denominator we cube root the y cubed and get y. Alright, rationalizing the denominator here. So a little bit different when the denominator is something like a 9 minus the square root of 2. We have to use its conjugate, so 9 plus the square root of 2, and of course we have to do the same thing to the numerator and the denominator. In the numerator, it's not too bad to just distribute the 4 through. We get 36 plus 4 square roots of 2. In the denominator, there is a pattern there, but if you have any sort of trouble with that, I would recommend just foiling or boxing this out. Again, the box allows me to kind of show you what we're coming up with. So the 9 minus root 2 times another 9 minus a root 2 looks like, again, I forgot my negative, or sorry, that's the 9 plus a root 2. So that's why I didn't have a negative there. So we get 81, 9 square roots of 2, negative 9 square roots of 2, so those cancel, and then a minus 2. 81 minus 2 is 79, and so that's our denominator. There is a common factor in the numerator of a 4 that you could factor out, but there's not a factor of 4 in the denominator, so no sense in going to that trouble. For number 22, we want to express that in lowest terms. We would start by simplifying that square root of 40x cubed. So we can pull out a 4x squared, because we can square root that, leaving us with a 10x here, which again we know we can't take any more out because 10 doesn't have any perfect square factors other than 1, and x, the degree is 1, which is less than 2. When we do square root the 4x squared, we get our 2x, and we end up here. Notice that we've got x's in both of these factors here, so we can factor that x out. And then there's an x on the bottom, so those cancel out. In the numerator, you could have taken a 2 out as well, but there's no factor of 2 in the denominator to cancel that with, so I wouldn't necessarily do that. If you had taken a 2 out of the top as well, you would have a 2 and then a 5 minus the square root of 10x all over a 5. So again, nothing really happens at that point, so either way is fine. I would probably just leave it like I had it originally. And then number 23, we get into solving equations. So remember, the first thing we want to do is try to isolate the radical that we have. So I added 9 to both sides. And then the reason we want to isolate that radical is so we can get rid of that by using the power property. So we take both sides to the second power. On the left side, that just gives us 4x minus 1. On the right side, we get 81. We add the 1, that's where we get 82, and then divide by 4, we get 20.5. You should always check your answers when solving equations, and especially when you're dealing with radical equations, because by squaring both sides of an equation, it is possible that you can introduce an extraneous solution. Again, you really have to check to be sure if it's extraneous or not, but something to be aware of. All right, last couple of questions then. We've got number 24. So we've got our equation similar to 23, except now when we subtract the 5 from both sides, now we get an x minus 5. We still want to square both sides of that equation. Again, on the left it's pretty simple, we get x plus 7. On the right, again, I didn't box this out for you to see if you want to do that or FOIL it or however you want to figure that out, but when we square x minus 5, you do get x squared minus 10x plus 25. Again, there is a pattern there. If you know it, that's great. If not, I would recommend continuing to box or FOIL that. We do end up with a quadratic equation, so we do want everything on the same side. That's why I subtracted the x and the 7. When we do that, we get x squared minus 11x plus 18. That does factor as x minus 2 and x minus 9, which would then leave us with solutions of 2 and 9. Now, spoiler alert, the x equals 2 is an extraneous solution. Again, you can check that by plugging it back into the original equation and seeing that the 2 does not work. If you do plug the 2 in here, you get the square root of 9 plus 5 equals 2. So 3 plus 5 equals 2, which of course is not true. The other way that I check that is I look at what I squared. I squared x minus 5. Well, x minus 5 would be negative if x were 2. So a couple different ways to check that. The 9 works out just fine. So that's why 9 is the only solution we have. Again, when we do this type of question, though, I am looking to see that you found the extraneous solution you were supposed to and the actual one, and that you did discover that that was extraneous, so you crossed that off. So I am looking for all of that when doing these questions. All right, number 25 gets to be a bit much. We have, and part of that reason is because we've got 2 square roots. So we want to isolate one of them to get started. In this case, with the minus here, it makes sense to me to add that square root of x plus 1 to both sides. So we square both sides then, we get 2x plus 3. And again, it gets a bit complicated when you're squaring something like this. So I boxed that out over here. You can see how when we multiply those radicals together, we get just x plus 1. And then with the 1's here, it's not too bad. Square root of x plus 1 a couple of times, and then a 1. So really looking at, when we put that together, an x plus 2 from here, and 2 square roots of x plus 1 from here. Going back to the main problem, so that's my right side, the x plus 2 and then 2 square roots of x plus 1. Left side, again, just the 2x plus 3. Next, our goal is to try to isolate that 2 square roots of x plus 1 as best we can. So we subtract the x and the 2 from both sides. That gives us x plus 1. Now when we do that, we still have a 2 here. In this case, I wouldn't divide by anything because I don't really want to create fractions over there. Again, you could do that and then just deal with the fact that it's a fraction, but generally people have kind of a hard time with that. Again, squaring something like x plus 1, make sure you're careful when you do that. A lot of people get that wrong, so if you need to box or FOIL it, that's perfectly fine, but you do get x squared plus 2x plus 1 when you square that x plus 1. Squaring the right side here, just make sure you square the 2 to get 4, and then really just canceling out the square root. Distributing the 4 gives us 4x plus 4. We do have a quadratic equation, so we want everything on the same side. That's why I subtracted the 4x and the 4, which then led to x squared minus 2x minus 3. That does factor, is minus 3 and plus 1. So the solutions appear to be 3 and negative 1. Checking those in the original does turn out that both of those do work. Again, when we square multiple times, I do tend to just go back to the original equation to check. If you do plug that 3 into the original equation, you get the square root of 9 minus the square root of 4 equals 1. So 3 minus 2 equals 1, which works. And if you plug the negative 1 in, you get the square root of 1 minus the square root of 0 equals 1, which also works. So again, always good to check your answers, but especially when dealing with the possibility of extraneous solutions. Well, thanks for watching, and hopefully this was helpful. Feel free to ask any questions that you still have.